Can you continue here? So I don't think we said this last time. This is for... Yes, thank you. This is the right-hand grip rule, not the right-hand solenoid rule, which I was ignorant of last time. Okay. So, if you have a conductor and there's a current moving through it, okay? Sean, you're looking at me. If you have a conductor and there's a current moving through it, it creates a magnetic field around it. The direction, we would like to know, is it going this direction or maybe it's going the other direction? The way we can tell is by using our right hand. If we put our right hand so that your right hand is this one, yes.
Your right hand.
No, the other one. The other one is the right hand, this one here. So, if you put your hand around the conductor, the direction of the magnetic field should be the same as your fingers. So it's going around this way here. As long as your thumb is in the direction of the current. Okay? Do your very best to draw this in your notebook, please. This is the right hand grip rule.
And left hand.
It doesn't need to be beautiful. It just needs to be understandable.
No, we should be perfect.
No, nobody's perfect.
High education.
No.
It is perfect.
We have perfect shot.
Uh-oh.
Oh, Sean. What?
Wonderful. Gorgeous.
Show me your gorgeous, wonderful picture.
Show
Show me your gorgeous, wonderful picture.
Tell me it's gorgeous.
It is gorgeous and wonderful.
I can have 4 fingers.
That's okay.
Wonderful.
Yes.
Yeah.
Okay, continue.
It's so hard, yeah.
I said it doesn't need to be beautiful.
I think Victoria very good.
I'm really
Yeah, actually, I think you're right.
perfect.
You mean?
Wow.
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 Genius.
Guys, I need to continue.
Okay,
I need to continue. Okay, so to give the definition, a solenoid is a coil round in a tightly packed helix. That's all a solenoid is. So I'm really just giving you synonyms here. A solenoid is a coil like this, and it's tightly packed. What I mean by tightly packed is it's like this, not like this. Okay? That's what tightly packed means. Tightly packed means like this, not like this. And coil means this shape. That shape is a coil.
I don't understand.
Which word?
Whole sentence.
Which word, Bruce?
Oh,
Really? Do you remember solenoid? We did that last time.
yeah.
And I'm saying coil is the name of this shape. And tightly packed helix means this, not this.
What is that?
Look, tightly packed? Yeah, Jinjin.
Okay.
So the material is not.
Is that not what it is?
Yes, but really in Japanese is another thing.
Oh, okay. Okay.
Japanese.
So the material, what's the material for?
The material just needs to be a conductor.
Oh, but I mean the material is not a fluid.
No, the material is, it's important for how well it works. I just need it to be a conductor. It just needs to conduct electricity. Yeah? Continue? Yeah. Oh, okay. Yeah.
Could you explain what is wound?
Oh, wound means this action. Yeah. It's the past tense of wind. Wind is when you, Jerry, like you would say you wind a clock. You know? Well, not anymore. Continue? Yeah. So, I kind of drew it already. So, in fact, so far we have said nothing about the units. You realise we've talked about magnetic fields now. We've said nothing about the units for, measuring magnetic fields. When we were talking about electric fields, how do we measure the electric field strength? What unit? Newtons per coulomb. But we said nothing about the magnetic field. So the way we measure the magnetic field, that is, how do we measure how strong the magnetic field is, or how much of a magnetic field we have, or where is the magnetic field? We use a unit called magnetic flux we don't use a unit magnetic flux. We measure something called the magnetic flux. That's what we measure. What exactly is the magnetic flux? The magnetic flux over an area of space is just a number of magnetic field lines. Before you write that down, let me just draw that. Here's a magnet, north, south. And which direction does the field go? From north to south, yeah. So maybe I'll just draw it like this, for example. If I make a little square here, I can say the magnetic flux here is just how many lines go through it. So it's 2 here. And we call that 2 Webers, meaning 2 lines. So the SI unit for the flux is the Weber, and it's how many magnetic field lines pass through the space. In fact, recall that I said you can always simplify your units into the basic 7 units. Remember the basic 7 units? Meters, second, kilograms, what have we got? Candela, Kelvin, and so on. You can always simplify. If you're curious, the Weber actually simplifies down to a volt second. Now, 2 things to say before you write this down. Number 1, the definition I gave is the simplest definition I could find. The precise definition is too difficult for this course. The precise definition involves actually advanced calculus. Also, for the exam, they don't ask the definition of this because it's kind of a bit difficult. But we do need this definition for the rest of the chapter. So the magnetic flux is just how many field lines. Now you might then ask me, how do you know how many field lines? You know, and the answer is, I'm not telling you.
How many lines in the unit?
How many lines? Now that's another definition we'll do. For this definition, it needs the area. So for example, I could say here, this is 2 Webers, but here, for this one, is 1 Weber.
Yes.
And here, well, maybe not here, but here,
No Weber.
0 Webers.
Yeah. This still have this all.
Yeah, like maybe it'd be 0.1. But then you might say, well, how could you have 0.1? Because the definition says you count how many field lines you have. See, this is the problem with the definition. The definition is too simple, but the real definition is too hard. So I have to go with this definition. So the definition is the magnetic flux is the number of field lines. Okay. As Jerry realized, it actually matters what the area is. And we don't usually like this in physics, because when you think about, for example, pressure, we say pressure is force per unit area.
Yeah.
So we'd like to do something similar here. Rather than saying the number of field lines per area, we should say number of field lines per unit area. So this leads us on to the next definition, which is called the magnetic flux density. And the magnetic flux density at a particular point is the amount of flux per unit area. In other words, the unit called the Tesla, and this is how many Webers per meter squared. So remember, for example, if I draw a comparison, the Pascal is how many newtons per meter squared. The Tesla is how many Webers per meter squared. Can you see the similarities? For pressure, you also care about the perpendicular force. For this, you also care about the perpendicular Webers. So as a formula, it's flux density is flux over area. Which part? Per unit area? Oh yeah, because the magnetic field could be hitting the area at an angle. So we look at the cos component and the sine component, and we actually only care about the Webers, the field lines that intersect at right angles. So for example, maybe it's 5 Webers coming in at an angle, but when you resolve the components, you get 3 Webers and 4 Webers, so you would just care about the 3. Alright. No, still writing.
What's the unit name called
The person, yeah, I believe so, yeah.
the Weber too,
Yeah.
and the Tesla, I can see.
It's also a person. Tesla.
Only
Just like
for-
that.
Tesla's a person, yeah.
Tesla is a monster in.
It's also a car company, yeah. The car company named after
the
Tesla person. And of course, Tesla is an electric car company.
Yeah.
Yeah, correct, yeah. They make expensive sports electric cars. Yeah, like their electric cars are like sports.
But they have a regular car.
Do they?
Yeah.
Yeah. Do you know the name of these doors? I know the name of the door when the door opens up like this. Wing, like a bird.
Oh.
Wing doors. Wing, like a bird wing. W-I-N-G.
Window. And a window.
Windows.
Okay, continue. Bruce,
Huh?
continue.
Yes,
Okay. Formula, okay. Okay, continue. Yes?
Okay.
Yes? Okay. This magnetic flux density is the thing which we have that is nearest to the electric field strength for the electric field. What I'm saying is the B is kind of like the E, although it's not really because it's different units. The E was newtons per coulomb, whereas the B is Webers per meter squared. But it's the thing that's nearest to it for the electric field. It's the most similar to it. Okay. So, a moving charge will produce a magnetic field. And in fact, we can find the direction using the right-hand rule. If the moving charge is placed in a magnetic field, it will feel a force. Think about it. Here's my magnetic field. Now, if I have a little charge here, let's say a little electron, as that electron moves, it will make, actually let's just make it a proton. As this proton moves, it will make a magnetic field. By using the right-hand rule, I can draw the magnetic field like this. It'll go around it like that. Move around like this. So what happens when you have two magnets together?
Push.
Well, they'll either push away or pull together. In other words, this proton will feel a force. So as this proton moves in the magnetic field, it will feel a force. But here's the interesting thing. If I put a proton here, I just come along, gently put a proton down, to be careful, they're quite small, and just let go, nothing will happen. Because if this is not moving, it will not make a magnetic field. If it will not make a magnetic field, then it doesn't interact with this magnetic field. So interestingly, it only has a force if you throw it at the magnet, because as it moves in, it makes a magnetic field which perhaps pushes it away. But if I just place the proton and move my hand, nothing happens. This is a very interesting force. It means the force only acts if it moves. So we have a charge will feel a force, which we know this. North will repel north just like S and S, but N and S will attract. Yeah. So we would like to know how much force will the charge feel, the small charge Q. The answer is the force F on a charge Q in a magnetic flux density of B while moving at velocity V. We have to have a velocity, we have to have a magnet, it must have a charge, so what is the force? The formula is quite simple, you could almost guess it. F equals QV times B. Now you might be wondering, why did I put the times here like this? This is actually a special multiplication, not a normal multiplication. Because if you think about it, V is a vector, velocity is a vector, and B is also a vector because it's the direction of the Webers. So this is a special multiplication, which I'll explain in a moment. But just for now, I'll call it a cross product. This is a special type of multiplication, which I'll explain in a moment, but I need you to write down this formula. Just write down the formula is F equals QVB. Now why is it a special multiplication? Let me explain. Let's imagine the Q, let's say the Q is 1 coulomb, okay? The Q is 1 coulomb. And the V, let's say the V is 1 meter per second. Yep. And let's say the B is 1 Tesla. Therefore, what is the force? 1 Newton. But we do not know the direction. Maybe the Newton pulls it in, or maybe it pushes it away. We don't know. This special multiplication tells us the direction. It's called a cross product, and you find it by using what's called Fleming's left-hand rule, which I show on the next slide. So, if you want to know the direction of the force, you put your hand in this position, the left hand, you put this finger in the direction of the B, you put this finger in the direction of the I, and this is the direction of the force. Yeah? So for example, if the B is pointing this way, and the proton is moving this way, then the force it feels will be upwards.
You should do the left hand, right?
This is Fleming's left hand rule. Yeah. Like this. No, left. Left. Have you've probably seen this rule in school before. Yeah. What, Bruce, what's wrong? Yeah, if you want, but I prefer, it's very easy to remember. FBI.
FBI.
Force. B. Current. Yeah. FBI.
Oh.
No, FBI. Okay. Continue?
Yes.
Yep.
Oh, you have to draw this.
You need to write something down to remember it. So you could write down FBI POW. Yeah. Got that?
Yeah.
Okay, continue.
No. Oh, you got tried it.
You're going to draw it?
Yeah.
Oh, it's so hard. It's fun.
It's very cute.
No, I'm sorry, you'll have to get the picture later then if you want to draw it. I need to go do some examples before we finish. Right, here's one for you to try. A bar magnet has a flux of 2 Webers at a particular point in space, and this point in space is actually a circle of radius 1 centimeter. What is the flux density? So use the first formula I gave you. Flux density equals... no, flux over area for flux density. So what would it be in this example? What would you have? 2 Webers over, very good, pi r squared. Yeah, because I tell you it's the area is a circle. There's 2 Webers going into the circle. So the answer is 6,366 Tesla. 6366 Tesla is the answer. Yeah. Continue. Yeah. Okay. That's okay, isn't it? All right. A proton moves towards the east in the Earth's magnetic field. What direction is the force due to the field? So let's draw that one, okay? Here is North Pole, where Santa lives, south, east, and west. Now remember, this is sneaky. On the Earth, the magnet's actually, it's the other way around. So this is actually like the south end, and this is like the north end, which means the field is going this way. Okay, so this is the direction for the B. I say a proton moves towards the east. So the proton is moving this way. So using which left-hand rule? F, B. Okay, so B is up, I is right, so F is towards me. On the graph, the way you draw towards, does anyone know it?
Triangle.
No.
No. Circle and the
Circle, sorry, the other one. Circle and a dot.
off.
This means the force is coming to me. By the way, what way do you draw it to show the force is going into the page? Across.
Oh.
Yeah. If you didn't know that, it's worth remembering. This is into the page and this is out of the page. And this is the answer here for this one. Now, the way you remember this is you picture it. Do you know how to remember this? You picture it like a dart. It's hard to draw. You know the darts that you throw? So when you look at the dart coming towards you, you see this.
Yeah.
And when you look at the dart as you throw it, you would see this.
Yeah. Wow.
That's how you can remember. Yeah? Yeah. No, when I heard this, I was watching a YouTube video and I heard this, I'm like, oh, this is really smart. It's easy to remember. So all you have to do is picture the dart. Yeah?
Why out?
Oh, from using this.
Yeah.
Did I do it the wrong way? Hang on. B is, if I look here, KJ, this is the way it goes, isn't it? F, B, I. B is up,
Yeah.
I is right, so F is out.
Okay. So that means direction of F.
Yeah, sorry, that's F.
I can't.
Guys, just to say, for this one here, okay, which direction is east in this room?
Where is
East is towards the city centre, isn't it? So it's kind of,
yes.
it's kind of this way, okay. So what I'm saying is, if I had a proton, and I fire the proton to the east, the Earth's magnetic field will cause the proton to move, let's see, out. This is me looking down, so it would go like this. This picture here, guys look, this picture here is me looking down at it. You know, north, south, east, west.
Yeah.
Proton goes this way. Out means then the proton goes up. So what I'm saying is, if I had a proton and I fired it to the east, its path would be this way, heading upwards. Yeah. Now, that force is going to be really, really small because the Earth's magnetic field is really, really weak. So you couldn't measure it in a lab, but it would be a very small upward force caused by the Earth's magnetic field. But it is measurable. Okay. Let's see, I have one example left. An electron enters a magnetic field. Someone's waiting outside. Oh, there is. What class have you got in here?
EAP.
Oh, okay, good. Give me a knock when the teacher arrives, okay? Thank you. An electron enters a magnetic field and then experiences a force. The magnetic flux density is is 250 millitesla. The electron is moving at 1/10 the speed of light. What is the acceleration? Okay, this is not as hard as it looks. How can I find the force? F equals QVB. Do I know the Q? Yeah. Do I know the V?
Yes.
Yeah. And do I know the B?
Yes.
Yeah. And I don't want the force, I want the acceleration. MA. So the answer is just going to be QVB over M. Okay, let's just... is it even worth putting it in? You know the Q, it's the electron, that's E. What did I say the V was? 1/10. So C over 10. The B I said was 250 millitesla, so that's 0.25. And the mass is the mass of a electron, which is constant number 3. I don't need to type that in. So this lesson is not too difficult. If you need to, these are the questions if you want to take a picture, or I'll upload them later today. You can get it from the video. Yes?
What is C?
C is 3 times 10 to the 8, approximately. Which EAP teacher do you have now?
Okay.
Okay,
What's up?